Welcome. My name is Peder Rand. I work at TI. I'm the director of ecosystems and standards for wireless. I also work on technology strategy. And I'm based in Oslo, Norway. So welcome and thanks for joining this session. I'm going to talk about Bluetooth channel sounding, which is ranging distance measurement between two Bluetooth devices, really any two Bluetooth devices. Which is new to the Bluetooth standard and a really interesting concept, kind of a holy grail for us that we've been working on for many years. And I'll talk a little bit about how we combine that with another technology that we're heavily invested in now is machine learning at the edge. So the combination of channel sounding and getting machine learning to do some of the signal processing in the tough environments. So first, I want to apologize. This presentation was made with a little bit of a bigger screen in mind. So if you find yourself in one of the back rows and not able to see everything, please feel free to move forward. And then we'll get started. So we'll talk a little bit about the use cases for channel sounding. So this technology allows measurement between any two Bluetooth devices, and that kind of comparable into some of the other technologies I'll talk about. But what it does is it brings it to devices that are kind of already existing. So devices that we've been already shipping for a while are capable of doing this new technology through a software upgrade. So it's available pretty broadly from us and from some of our competitors because it's all standardized. I think we've been working on it for something like 6 years now. Contributed a lot of IP into the Bluetooth standard and figuring out some of the challenges that arise when you move from theoretical distance measurement and signal processing through to actual environment and deployments that we're working closely with some very large customers on now. So it's an exciting time. One of the key things is it's also available on phones. So that one Bluetooth device that could easily be a phone that then measures the distance between the phone and anything else, or between the person holding the phone and some infrastructure that you're interested in. So it opens up a broad set. It started out in car access, digital key, passive entry, passive start, making sure that you can have a seamless experience walking up to the car with your phone and everything turns on and opens up as it should. We also see applications in building automation, very similar kind of use cases with the door, right? You're walking up to the door and it just opens up as you approach it. And we also see in tire pressure monitoring, just figuring out which tire is placed where on the car. We see it in all kinds of asset tracking and location services. And there's some really neat ways that we can leverage multiple units to figure out a sort of a 3D positioning as well of any device. So and that also has applicabilities in places like this with indoor navigation, where you can easily deploy solutions to query where am I really on this floor plan, because it is sometimes a challenge. So in comparing it to some other technologies that also do wireless ranging, the closest comparison is with ultra-wideband. So ultra-wideband is a very well-established technology developed many, many years ago. I think most of it over in Dublin, actually. And gives very good accuracy, less than 10 centimeter accuracy every time. It's brilliant for that. But it comes with some disadvantages within the power usage. It's very wideband signal and operating in high frequencies. And comes with some very challenging requirements then on the system that drive the cost up. So overall, it's a great technology if you really need that high accuracy precision positioning. But we find that in a lot of use cases, it's not about those last centimeters. It's about within a meter or so, understanding where a device is located, and then it's really exciting that we can offer this at very low cost. I think we have a 1K unit price of less than $1 for the simplest device that can do this. So it's really bringing this into a host of applications that can't carry the cost or power consumption of ultra-wideband. So when we started looking at this, figuring out what the use cases are going to be, one of the key areas that we looked at was also in the asset tracking space, and hospitals is a key one. But they also have several other use cases in hospitals with proximity of how close are you to some machine that you're trying to operate, with tracking the devices that should not be able to move outside certain areas. And then also we have car access and also access to the doors. For us, it's kind of a good illustration of like how many channel sounding use cases can be within just one environment that is hospitals. So this was a good inspiration for us when we started out. And now it gets difficult because I'm going to explain some of the basis for this technology. So we have two techniques in channel sounding, and they're generally used together. They have some different properties. So you have phase-based ranging, which gives the accurate ranging. And then you have round trip time, which is actually measuring the time it takes to send the signal across the length that you're trying to measure. So that's actually measuring the speed of light. And it's extremely challenging to do efficiently. One of the things that's good about this way of doing it is we do it both ways. So you get your time of flight going one way, some time for the other device to send the packet back, and then you get the time of flight again. So you actually get the time of flight twice, and you half your error, basically. So we get it reasonably accurate. And the reason this is important is mainly for security reasons. This will come apparent when we walk through the phase-based ranging, which is the more difficult one. Because here we're actually there's an initiator. One of the Bluetooth devices starts, and it sends a packet to the reflector and starts to set up, synchronize, and make sure that they're on the same frequency. And the next thing that happens is that the initiator takes its local oscillator, so it's 2.4 gigahertz oscillation, and it uses that to send a packet. And the packet is just a sine wave. It's just the carrier wave going, just like a sine signal, to the reflector. The reflector receives it, and it compares the phase of the incoming signal to the phase of its own local oscillator. So those two oscillators are not necessarily in phase. But what you get is essentially a measure of exactly where on the sine curve is the wavelength of the 2.4 gigahertz signal hitting the reflector. And that wavelength, the phase of that wavelength is a measure of the distance inside of one wavelength that you are away. So that doesn't give you any information about how many wavelengths have gone up and down from the initiator to the reflector. But it does give you an indication of exactly where on that wavelength you hit. And the next thing that happens is the reflector takes its own local oscillator and sends the signal back to the initiator. And the initiator does exactly the same thing. It compares the incoming signal phase to its own local oscillator phase, and then gets an offset. And the beauty of this two-way communication is that by doing it this way, you can actually, by pure math, you end up eliminating the phase offset of the two local oscillators. So you don't need to synchronize the phase between the two devices. They just need to be at the same frequency. So it's a very elegant solution to something that is generally a big challenge with phase measurements. Just by doing it one round, you end up eliminating the biggest synchronization problem there is. And as I said, this doesn't give you, at this point, any information about how many wavelengths you are away. And that's, of course, what you're interested in. So what you have to do is just repeat this measurement on many different frequencies, because those frequencies all have different wavelengths. And what you end up with is a pretty significant set of data over frequencies, both the data that is at the reflector and the initiator, and you end up with a curve that's, the frequency, the phase offset. If you map the phase offset against the frequency, you get ideally a straight line. And that straight line, the slope of that straight line is the distance that you are away. So that's kind of magical. I'm not going to go more through this today, but there's a very good paper on it on the TI webpage. And I just put the title up there so you can easily search it. And that gives more details about this. So the phase-based ranging has a challenge, as I mentioned. There's a reason why that's not enough. The round-trip time is needed because the phase-based ranging, that slope of that curve, as I talked about, after 150 meters, it rolls over. So it actually, a device at 10 meters will send off the exact same signal as a device at 160. So to compensate for that, we also do this time of flight, measure relatively inaccurately the time that it takes the signal to go back and forth. And that's more than enough to understand if you're 10 meters away or 160 meters away. So between those two data points, you have a very good understanding of where you are. And I'll just show the procedure. This first step is called mode 0. This is the initiator, one of the Bluetooth devices, making contact with the reflector, and they send back and forth some packets and communicate on, okay, how are we going to do this, right? Different types of capabilities that they have. But they also, very importantly, look at each other's offsets or frequencies. And the initiator compensates its local oscillator to match the exact frequency of the reflector. Because you will have different crystals on both sides. There will be maybe a little bit different temperature, some other variations. So very importantly, synchronize the frequency, because that needs to be exactly the same, even if the phase is not. And then you move over to mode 2, which is the phase-based ranging. And you perform over 72 different frequencies, for example, in the BLE space, a range of measurements, send all the data from the reflector back to the initiator in this step here, and then you get to post-processing. Because then you're left with all these measurements that are done over a wide range of frequencies, maybe a couple of different antenna paths, and you have to make sense of it somehow. And that's, there's no supercomputer sitting in the initiator usually. It's a normal BLE device. So how do we deal with that? Because usually, if you take that data, after you've done the channel sounding procedure, it takes about 16 milliseconds to do the full number of 72 steps, 72 different frequencies. It take about 3.7 milliseconds to transfer all the data back from the reflector to the initiator, so you're left with all the data in one place. And then you have to crunch that data. And if you do that with the standard algorithm, which is called music, then you end up with about half a second of processing time on a 100 megahertz RISC processor like the Cortex M33. And half a second is noticeable in human interface scenarios. It'll seem sluggish, right? So how do we get away from that? And by the way, there's an energy consumption aspect to this as well. It'll use 20 times more energy just doing the calculation than it is actually doing the transmissions back and forth to do the measurement. It's a pretty big problem. So what we came up with was, let's put these calculations, we know exactly what they are. We know exactly what the processor needs to be doing. So we made a dedicated processor called the APU that we put into our new devices in the CC27XX family. And this processor does that extremely well, so that we end up in a situation where it reduces that time it takes to do the post-processing down to 15 milliseconds from half a second. So it's of enormous importance, of course, to the latency, but it's also of very significant importance on the battery consumption, because this is also a much smaller processor than the Cortex M33. So by having dedicated hardware to do these calculations, we end up with a very significantly improved user experience and power consumption. So let's look at some real-life scenarios. This is a picture from any sort of normal parking lot scenario. This happens to be the one in TI's Oslo office where I work. It's an uncommonly dry and sunny day. But we were able to go out and do some measurements. And this type of environment is very simple, right? You have a straight path, line of sight between the two nodes. And you also have generally then a reflection through the ground, maybe one reflection from a bit further away from those cars, but it's a pretty simple radio environment. Not a lot of multipath, not a lot of other paths bouncing around. So the music algorithm that we talked about, it does very well in this scenario. We get, within the 80% of the samples, this window here, we get to less, than 10 centimeter accuracy by just conventional methods and good hardware. So as we talked about, depending on the distance, we get to somewhere between 15 and 20 milliseconds of processing time. If you go up to some 25 meters of range, then the processing time is around 25 milliseconds. So the amount of time it takes to process increases with the distance as well. But of course, when we have dedicated processing, it's still pretty fast. And in this scenario, what we're also doing is we're having multiple antenna paths. And I brought this board along to show you what those red things look like. It's just your standard BLE development board, but it has a dual antenna plug-in board so that we have two antennas on each side. So that gives us a total of 4 different paths for the RF signal to take between the antennas. So it's a 2x2 antenna configuration. That just gives us more data. And when we get that more data, you get better accuracy, but you also increase the time it takes to process all that data afterwards. So it's a trade-off. In this scenario, one antenna would be sufficient in most cases. But it's not always as simple as this. If we go and bring this indoors, and here we were able to do some more testing because it was more comfortable and warm. But this is inside the office. Then we take the same 2 boards, set it up, distances between 0 and 10 meters. And if we look at this green line here, that's with the same configuration of 2x2 antennas communicating. And you get more data. And in this scenario, we have more complex reflections from the ceiling, from the wall doors. But you also have interference from the Wi-Fi. You get interference from the phones that are out there for the people working. So it's a much more complex scenario. And one of these nodes is also behind one of the doors. And you see that the error with traditional processing gets to be in the 80 percentile again, around 60 centimeters compared to the 10 centimeters that we were getting outside. And then if you simplify, and for the sake of just a quick test, we took with just one antenna path. And there you see, when you get to the 90th percentile, it kind of drops off in accuracy and starts overestimating by almost 2 meters. So there is significant improvement in sort of a challenging environment to have two antennas on each side for the channel sounding to eliminate some of the toughest problems with the multipath and interference. But it's still, in a 10 meter range and an accuracy within half a meter or 60 centimeters, it's still useful and can can be a good part of figuring out where something is. But there are scenarios where it gets really difficult. And the biggest nemesis is actually people who put their phone in the back pocket for some reason, and then they walk towards their front door or their car or something, and they expect the ranging to work well. And what you're doing is essentially you're putting like a sack of water that has a resonant frequency of 2.4 gigahertz, and you're putting that between the device and what you're trying to measure against. And I mean, if people knew this and had some kind of empathy with us, they would just quickly agree not to do this because of the alternative has been brutal. We've spent man-years solving this issue, and very happy now that we've finally found a decent solution for it. But it would, of course, have been much simpler if everyone just agreed to put the phone in the front pocket instead. We wouldn't have had to deal with this. Because the big issue is you take the direct path for the signal, goes through your body, essentially gets attenuated to very, very low levels. And what the receiver is going to see is all the reflections coming from the ground, coming from the walls around. And we end up with a very tough, the set of data that we get is really messy. Like really messy. So the traditional algorithms are not able to make any sense of it. So what do? We know that machine learning can make sense of things that seem senseless if we just train it well enough. So in comes machine learning. And of course, we had thought about this. So this little processor thing that we put in there can also do neural network inference. So once the situation becomes complex enough, you need to be leveraging something as complex as machine learning to be able to extract that information from the complex signals. And another advantage with machine learning is you can train it for a specific scenario. So if you have, for example, a door lock, will be a very different RF environment from something like a node that's inside of a car. Or if you've got your little find me thing that you're left behind the couch or something. That's also going to be a very different scenario. From an RF perspective, it's generally not going to have much metal around, or versus the door lock, which may have a lot of metal. So you can take those individual scenarios and you can train the machine learning algorithm to work specifically well in those scenarios, even when the customer is using their back pocket to hold their phone. And the reason why we do this, not sort of in a server farm somewhere, right, and do it on the edge, and actually in the device and in the radio, is because of these two advantages. You have the latency aspect that we talked about. We can get the calculations quite quickly, within 15 milliseconds typically. And the other aspect is the power aspect, because we don't need to send that data again further on to the cloud and wait for it to come back and then receive the transmission again. It uses radio resources and takes power. So there's great advantages to being able to calculate this on the edge. And what that gives us is we're at about 2 times the accuracy compared to a scenario where, in a complex scenario, machine learning doubles the accuracy compared to a traditional algorithm. We generally use this one, Music. There's another one called IFFT. It just runs a lot faster, but it's much less accurate. And then with machine learning, you've got a very significant 50 times improvement on latency. So the machine learning algorithm actually runs faster than music. But in the very simple scenarios, the music algorithm still performs better. So how do you deal with that? Because you don't want to train something to work well in an open environment where there really is no problem. That's just a mathematical operation to get the distance. In that scenario, so we have devised a quality metric. So you look at all the incoming data, take a quick scan through it, and assess very quickly what's the quality like. Because if the quality on the incoming signal is good, no need to use the neural network. You pass it just through the music algorithm. And since these run in the same processor, it's very flexible. So we can decide based on the scenario, is it someone walking towards the door with the phone in their back pocket? We use neural networks. If it is someone, just walking towards the door in a normal fashion with the phone in the front pocket, it uses music and gets slight improvements on accuracy. So, in summary, multiple antenna paths can be an improvement, especially if there's a multipath environment. Music enables the best possible accuracy compared to other algorithms and also to machine learning. But once it's a complex environment and a challenging RF situation, machine learning does significantly better, 2 times. And having this mathematical coprocessor, the APU, and the reflector device specifically that's doing the calculations is a real benefit, both from a latency and power consumption performance perspective. So, questions? I think we have a few minutes. And this is complex stuff, so I hope not everyone understood everything yet.
Is there any limit on how fast the object can be moved, given the time it takes?
Yeah, that's a great question. And it's actually very interesting in the context of multiple antenna paths as well, because once the device is moving, you actually get the advantage of multiple positions. So no, there's no real limit. We've tried anything that sort of has a human level pace, but the whole process that involves radio probably starts right around here. So I would say it's about 12, 13 milliseconds, and you don't move any considerable amount of distance within that time, unless it's connected to something very fast. So that gets 72 steps, and that's more than enough to do a calculation of distance. So if you move any significant amount of distance within the 12, 13 milliseconds, then it will affect the accuracy of the result. But for any kind of person moving around, it's not a consideration really. Yes.
See if this works. Yeah. So I guess you mentioned you've used machine learning to kind of train on specific situations. What happens if you're outside of one of those situations? Like, does the ML algorithm sort of degrade significantly? And I guess a follow-up question to that is, if there's a specific situation that we want to use it for that maybe you haven't trained for, do you list what you've trained it for, and can you also can we update the neural network? Yeah, so to address the first one first, I think what we're in terms of the environment that it's in, for most devices it's relatively static, right? And the RF environment around. I think where it changes significantly is if you place something on a metal surface. And that's also why especially when we're doing integration into different automobiles, and the placement relative to metal is something we generally want to take into account. You may get some degradation. This is, but I'll tell you, for every one of our automotive customers, they have so far received the same model, trained the same way, and we've gotten good results with that. But we see more as a future enhancement that we can train specific scenarios, but we're not set up for it yet. So it's more of a future enhancement, and the 2x improvement you saw there was without any specific training for the environment. But we believe we can get even better with some slightly more advanced models, but also training them very specifically for certain environments. So it's more of a future enhancement. Yeah. Yes.
Yeah, you referred to the mobile phone channel sounding being at the other end. How do you see that technology being adopted by mobile phone manufacturers so that it's going to be usable in that kind of scenario?
Yeah, this is one of those ones where I have to be a bit careful what I say. So, yes, it will be adopted in mobile phones. We've done, a lot of testing to make sure that will work well. But yeah, I can't get into any specifics, but that's coming as well. So, yes.
Is there any incorporation with the angle of arrival in terms of the ML to do the filtering on that and the improvement of that?
No, so in this scenario, we don't use the angle of arrival. I think, looking at a board like this, you could. What we found with angle of arrival is we need a board about this size with an array of antennas in order to be able to get to the accuracy that was shown here. And it's great for some scenarios where you might be limited in the number of nodes that you can place. But we think this is way more versatile, and we'll rather leverage the trilateration methods to find the position of the object rather than to rely on angles, because that spatial delta that you need for the angle makes it very cumbersome to deploy. Yeah. All right. We are out of time as well. Okay. Thanks, everyone. Appreciate it. And by the way, before you go, if you want to see more of this board or talk to the TI people, we're going to be down on the booth for the rest of the day. So I'm sure there are more questions as well once you had a chance to think about it. Thank you.